It's also helped in a number of other cases. So potentially even doctors. Their jobs replaceable by things like this. So diagnostic medicine, certainly, this can potentially do much more quickly and more accurately. So that's going to be interesting when that's spread to a wider number of conditions. So what about software developers then? So you might hope that we needed to write the code that this sort of stuff runs with. But as I said, kind of been playing about with how we could generate that code using artificial intelligence itself. So one approach you can take to that is using something called genetic algorithms. So these are a type of guided random search algorithm. So as opposed to a systematic search, where you just kind of go through your list of things until you find what you want, or a random search, where you kind of look over there, then here until you find the thing. In a guided random search, you pick a random place to look, and then you say, okay, based on what I found there, it kind of makes sense to look this way next. Obviously, that's if you're searching something that's in some way sorted in some fashion to start with. And in particular, genetic algorithms take inspiration from biology and notably from evolution. So there we have this idea of natural selection. So if you have some kind of adaptation that means you're more likely to survive, you're more likely to reproduce, pass your genes onto the next generation. And then there are some mutations, and if they create beneficial adaptations, again, that's more likely to be propagated. So we take that general flow for a genetic algorithm then. There's one key difference here, which is we now have an end goal that we're trying to get to. So this is where the analogy of evolution is kind of broken down. So what we do is we, rather than sort of survival by whether you're still alive, we construct our own fitness function depending on what it is that we want to get to. So let's say I wanted to search the space of all possible strings for a text string containing the name of this talk. So I would start off by generating a population of a number of strings, just some random ones, and then I would evaluate them according to whichever fitness function I've written. So in this case, it's going to be how much do these strings look like the one I'm trying to get to. And then I'm going to select some and allow those to reproduce to the next generation. So I'm going to select naively the top half that have the best fitness. Okay. And then we're going to cross those over. So this is analogous to getting half your chromosomes from each parent. So we could just take the first half of one string and the second half another and stick them together, for instance. And then some kind of mutation, so the same way that some of your genes in the chromosome get mutated, we're going to pick a random character in that resulting child string and we're just going to flip it to something else. We've then created a new population, so the next generation is going to consist half of the parents that we selected from the previous one and half of these children. At this point we're going to stop and we're going to check, have I got in this population any of the things that I'm trying to get to, so have I reached my target string? If great, I stop. If not, I loop back around and keep this process of selecting the ones that most closely resemble what I'm trying to get to and gradually evolving them over time. So let's try and look at that in action then. You cannot see that.
It's not mirrored.
How do I make that happen?
Settings, system preferences, display.
I've totally had a Mac for ages.
Yeah, you know what you're doing. This one.
Cool.
This one. This one.
Ta-da. Cool. Thank you, Corey. So, just run that again. Right, so I'm going to try and evolve some strings to talk title. And indeed, I've reached that. So if we scroll up, we'll see we started off with sort of just some fairly random looking strings. You'll notice they're still about the right length. That's because for each one generation we've printed kind of what was the closest match. And this is probably of the first generation being around about the right length we were looking for, got a reasonably high fitness score. And then over time, by selecting ones that most closely resemble what we're looking and crossing them over, we start to get towards what we're looking. So you can see the spaces start being in the right place and some of the letters get correct. And eventually we converge on what we're looking for. Okay. So that's very well for strings. How do I turn that into evolving some program code? So the key difference, or the key problem I'm going to have here, is whereas with the strings I could just generate some random characters in sequence to start with, and they might not be very close to what I was trying to get, but they were still a string. Whereas if I just dump a load of random characters into a text file and then try and run that through, say, a Python interpreter, the odds that that's actually going to be a valid program that won't just fall over are quite slim. So what we want is, do we want to find a language that we can write in, which is going to be have very few sort of syntactical rules. So it's going to be reasonably easy to generate something at random that actually will run. So you might kind of think, well, how am I going to do that? Maybe I could sort of use some kind of template. So I'll have like, this looks like an if block, this looks like a for loop, and kind of just fill in the gaps and stick those together. the problem you're going to have there is that when it comes to crossover and mutate, keeping it a valid program is going to be quite difficult. You might decide, well, I'm going to write my own language. I'm going to come up with some kind of symbols that mean various things, and I can just stick them together, and they'll be allowed in any sequence, so I can mutate them and cross them over. The problem you're going to have there is you're probably going to end up restricting what it is you can program in that language. So we want something general. We want to be able to evolve code that could do anything we want it to do, that is, as long as it's computable. So we need something. So we need our language that we're going to choose to not only be syntactically simple, but also Turing complete. Now, I'm aware that this is an open day with a wide range of things, so I'm going to take a brief second to explain what on earth I mean by that. I'm going to turn this back on. I have no idea how to put that back. If I hit play, will it just
speak notes?
Cool.
That'll still work.
Awesome. What do I have in my Turing complete? If we think about, so Alan Turing came up with the idea of a mathematical model for sort of describing general computation. So rather than having a machine which is, this does this one particular thing and never anything else, you have a machine which you can program to do one thing and then reprogram it later to do something else. And whilst thinking about this, came up with a mathematical model that we can use to think about this, called a Turing machine. Basically, you imagine an infinitely long piece of tape with a series of cells, and in each individual cell, you can write in a symbol, you can change the symbol that's written in that, or you can read out the symbol. And then you have an arrow basically pointing to the cell you're currently looking at, and you can move that along. And that's basically what it is. It sounds like a very simple machine, but if you can, you've got a computer algorithm, you can construct a Turing machine which will be able to simulate the logic of that. And when I say a language is Turing complete, I just mean that I can use it to simulate a single taped Turing machine, aka it can be used to simulate whatever computer algorithm I like. So I can program arbitrary things in it, basically. Okay, so the question is now, what is the simplest Turing complete language I can think of, which is going to give me this property of very simple syntax? So at this point, like any good developer, I thought, well, someone's probably solved this problem before, I will Google it. So I came across a blog post written by Corey Becker. So her site is primaryobjects.com. It has a load of really interesting articles about machine learning. And in particular, she'd thought about how to do genetic algorithms and evolve programs. So there is a very simple language which has only 8 characters in it, and which pretty much just simulates a Turing machine. So what is that language? Contrary to Corey's earlier advice about answering your own rhetorical questions, I'm going to give you the first 5/8 of the name of that language in the interest of keeping the talk age appropriate. The last 3 characters I've left as an exercise for imagination. So the first 6 symbols here are pretty much just the Turing machine stuff. So you can, you're moving your pointer about, you're changing the value in that cell, outputting and inputting. The last 2 are more noteworthy. So this is a property of the language that allows you to make decisions. So if I've got this value, do this thing, otherwise go do something else. So these are these square braces. So if you can either jump past the next brace or go back to the other one, but only if you have a certain value under the pointer. Okay. A brainf program might look like this, for instance, for Hello World. You can see that this is a fairly esoteric language. It's not particularly intended to do particularly complex programming in, because you would just rapidly get quite a headache, I think. However, for a machine, this doesn't matter. This is just as understandable to it as some Python code or some C code or whatever. Okay. So we are going to try and evolve some programs that use. I'm going to use Python to do the genetic algorithm, but the actual programs are going to be written in this. Right. So the program I'm going to do, I was going to do Hello World, but I realised it would take too long to converge on a solution for the time I have left in this talk. So we're going to do an abbreviated one. It's just going to say hi. Right, so as the thing starts running, the thing starts running down, bear in mind the thing we're evolving is the program itself in brainf. This is going to be printed out once per generation, the best one. Most of the output that's appearing is going to be the output of that program. So you might get to a point where you think, that's looking really close, why hasn't it just got there? The actual underlying program might be still quite way off. Okay. So, new things we have to worry about here. So we see some timeouts. So it's possible to generate a valid program that, for instance, never terminates. It's stuck in an infinite loop. So we have to be able to detect that, give it a bad fitness score. As you see, some of the output gets quite carried away. We equally have some programs that will be invalid. They haven't matched up those square braces. It's pretty much the only thing you can do to make your brainf code syntactically invalid. We might have programs that go off the end of the memory of the tape that we're using. So all of those things get given a very low fitness score. So what's remaining is we quite quickly get to things that at least produce some output, and then we give it a higher fitness score if that output is closer to what we're trying to achieve, so if it's closer to saying hi to us. Now, it gets reasonably close quite quickly, and then it gets kind of stuck, because whilst the output might be quite close, the underlying program, you might need quite a big mutation to that. It might be stuck in a slightly awkward loop to get it to actually change what's being produced. And because of that, we need to have sort of greater options of more diversity in the mutations that we allow. So rather than just picking a random character in the program string, we potentially are going to go over the whole string and with some fixed probability maybe mutate each character. There are also other types of mutations now, so sort of inserting characters or deleting them or just sort of shifting the whole thing around. We also change our selection, so rather than just naively picking the top half, we don't want to get stuck in some kind of local minima where it's really close but it's going to take some big jump to the underlying code to change it. So we want to allow some of what appears to be a lower fitter individual, but might lower fitter, but might actually be very close in terms of the underlying code to survive through and reproduce. So we now make the chance that they will be selected proportional to their fitness. So some low fitness individuals might still get through. And this will eventually get to high. I've just broken the auto scrolling by touching. Excellent. What is another sensible thing to think about? Why did I touch that keypad? It does get there. So as you can see, that the local minima is a real issue now. So I should point out, at this point you may be thinking that C3PO is not bringing you your P45 anytime soon. Other people have made some of these that do more interesting, complex things. So Corey's blog post that I pointed to earlier, she's gone on and made evolved programs that do things like generate the first few Fibonacci numbers, or write out the verses of 99 green bottles of beer on the wall, green bottle, and that kind of thing. So there is kind of more interesting things going on there. Even so, I think there are probably limits to this approach, not least the kind of programs that it outputs are fairly suboptimal. So you'll notice there's lots of times where it's got lots of pluses followed by lots of minuses, where you may as well have not done anything. So yeah, there's that kind of issue. But yeah, there's still some really interesting stuff there. And yeah, and that's just genetic algorithms. You go into like the cool world of like neural nets and stuff, then we probably really are out of a job. So finally, I would just like to say thanks to my friend Brice for starting up that meetup group where I learned all about this stuff. It is really cool, and I would strongly recommend that you think about setting up one where you are. You should also check out his site, Decacoder, where you can learn programming online and stuff. Both beginners and experienced people, and not least because it uses a load of the cool AI stuff we've been doing over the year to individually tailor the experience to you and how you learn. And that is all I have to say.
All right, we do have time for questions. Yes.
Which is quicker, you writing that code to reproduce or it writing? Because it's probably that, right?
For something like, well, actually, yeah, for that, potentially. And that is the really interesting thing about doing it in BrainF, is that, particularly for anything more complicated than just bring output, it can genuinely write that code quicker than I can, which is really cool. I'm also really tempted to do stuff like, if you could get it to write the fitness function itself, that would be scary, because then you just can't do it at all.
Well, you could do this with BDD, right? You could write your BDD script
yeah.
and then just leave it to write the code.
That's what I was thinking, actually, combining it with something like Hypothesis. So like, you could write your code in this, and if someone finds a bug, you just write an extra thing to be like, oh, I now want it to do that, and leave it to evolve a bit more. It'd be really cool. Yeah.
What are the main bottlenecks for that program? Is it, CPU? Is it RAM?
Stuck that thing onto a Power 7 server.
Yeah, no, it would, I think what would be really interesting actually about putting it on a more powerful computer is I would really love to be able to run parallel things, because I think a lot of getting stuck in the local minima, if you could have isolated populations, they probably get stuck in different local minima, and then you could kind of bring them in as kind of like migrating an individual from this population to that one and see what that did to like how the algorithm moved on. I think that'd be really interesting. Oh, yeah.
Two questions. Is there any actual benefit to doing the crossover in addition to the random mutations? And would it be possible to apply this to a non-esoteric programming language by manipulating not just text, but some intermediate application like that?
Right. So the first one, the crossover, you don't have to do it. I mean, some species evolve they sort of don't pair up for reproducing, so you could still have the general principle and do that. I think quite a lot of how genetic algorithms work is it's this principle of you take two things that do something quite similar and quite close, but they're different. You cross them over and you get something even closer. There's some like maths there, which like I don't know, but it's you wouldn't necessarily automatically assume that would be the case, but it does seem to work. But yeah, I've done other algorithms where it didn't do the crossover and it worked. I've completely forgotten your second question, sorry.
Would it be possible to use this to write Python, say, but not by writing Python as text, but writing some intermediate representation like a syntax tree?
And then manipulating that.
And then manipulating that.
Yeah, I think you could. So I did some other stuff for as well as strings and programs evolution. I did evolution of functions, where yeah, that was kind of done by trees and crossing those over. So yeah, I think you could.
You try to model genetic algorithms. I'm wondering why. Are there different types of algorithms that will be also, let's say, effective in solving the problem of automatic generation of the code?
Sure. So the why was just we were kind of, for interest and education's sake, going through a load of different machine learning techniques, and it happened to be this one that I did the programming evolution with. I imagine that yes, you could use other stuff. I hear neural nets are really cool and crazy, scary, intelligent, so I bet you could probably do something there.
The examples you gave, there's no input, so basically the starting state is always the same. Is there anything in terms of, obviously, if you're starting to have your fitness function, which has got to be correctly based on a bigger starting state, you know, if you can have different inputs in the program, is it harder to work for it to work out what the correct solution is? Because you could end up where if you gave the program one string, it would be fine, so right, that's the solution. Then if you change the input, then suddenly it no longer terminates or something like that.
Oh, I see, yeah, because it generates some random things. Certainly, depending on what it starts off with, it will converge in time. So I've seen high work in about 2 seconds, and I've seen it take a scary amount of time for someone that's trying to demo it at all. So, yeah, I think you could conceivably start with something that might not terminate. Hopefully the mutations will be enough.
I've got time for one more.
So if you're matching just a string like hi or hello world, that you can be very explicit about what you want your program to do, but what if you have something less explicit? Like you mentioned writing 99 bottles of beer on the wall, but you don't have to type out all the verses just for it, because then you did your own job. So if you have a less explicit version of your intended output, how well do you think it could work?
I don't know. I mean, we still currently have to write the fitness function, so I guess we still need to know what we're aiming for. Are you kind of just meaning we want something that matches this rough pattern or something like that? Yeah, I guess we could do that. It would give you more possibilities of the potential output to get to, which makes me think that if there's more solutions to find, it might be quicker. But